let's move on to the actual meat of the course, which is OpenACC. So today, the goal is to understand the basic concepts of OpenACC. So what is the execution memory model? More or less, you had already an idea from the introduction, but how this translates to the actual OpenACC programming model. We're going to go walk through the basic directives. Then I'm going to present you the different profiling and debugging tools, which then I can demonstrate you on the examples. And then we're going to start our hands-on sessions, which basically exercises on these concepts. The second day, we move to a bit more advanced topics, starting from this synchronous execution of kernels and the weight queues and or the equivalent of streams. And techniques there for overlapping communication and computation. And then we're going to talk about how OpenACC can interact with CUDA code and how you combine it with MPI codes. And we're going to see also the concept of RDMA and how you can avoid unnecessary copies from the host to device. Then we're going to talk about the concept of deep copy, what it is, how this can be implemented on using OpenACC, and why this is important. And of course, we're going to have hands-on sessions at the end, exercising all this stuff. So the second day, the hands-on sessions are more, I would say, interested or more involving, I would say. So. Yes, but in any case, also today are quite, we're going to see some nice things. So what is OpenACC? As OpenNP is also OpenACC a collection of compiler directives, so that you can specify that loops to be offloaded to the GPU, and you can also manage their data. And the idea is that you can offload something from the host CPU to an accelerator device. It doesn't talk about, OpenACC standard is clever enough not to talk about GPU specific. It just says an accelerator device, it leaves it open. It can be anything from GPU, it can be, I don't know, in the future, an FPGA or whatever. It could be the multicore itself. It can be considered as an accelerator device. And so that's the idea. The programming model is, again, this host plus accelerator. So you have to take care of, in your model, of the data movements, although those may or may not happen. That's another story. And it's a higher level representation, as Marcus also discussed with you in the previous session. And the current specification is 2.6. Now I'm going to make a quick comment about the compilers because we're going to work with them, but Marcus will be more precise tomorrow. So the compiler support is now basically, at the forefront is PGI compiler, which always supports the latest standard. And then the Cray compiler supports up to 2.0. And they won't support more, but they just still keep providing support for their compiler implementation, their implementation up to 2.0, plus their additional features. And GCC, there is also a considerable effort in GCC to support. I think they, the last time I checked, they had a partial support of 2.0, or now they're complete 2.0. I'm not sure. But still is not so mature for the PGI compiler. As the PGI compiler is. So why to use OpenACC? There's several reasons, I believe. First of all, I don't care about all the details that I presented you before, which was only a small part of what's going on under the hood that you would need to know if you were writing CUDA. I just want to do my science. I want my code to quickly have my code ported to the GPU and be faster. That's one reason. Another reason is I want to run on accelerators, but I still need to have a readable code. I mean, I don't want to completely move away from what I have and not be able to recognize my code anymore. So I just want to do not intrusive changes. Another is I want portability across accelerators. The standard does not specify that the target device is a GPU. If another device comes up and another vendor implements OpenACC, in fact, the Tianhe supercomputer in China, which was at #1 place, they have their custom processor that they build their own, and they run OpenACC on top of it. The target is not a GPU, it's not an NVIDIA GPU, it's just another thing. So the same code could run also on a GPU, so that's portability. And it could also run on the multicore. Another common case, I think, lots of people in the science have encountered is when you start your PhD, your postdoc, you suddenly inherit some code, which might have been written, I don't know, 30 years before. And it's always gradually evolving, and you said it has been so large, and you say, oh no, I cannot refactor this thing, but I need to have my results faster, I need to modernize it. So that's another way to go. Finally, I mean, if you're programming Fortran, then it's always OpenACC is a good candidate, because you don't have to get, sorry for that, you don't have to get, okay, you could use CUDA Fortran, but you don't have to get into, again, fancy stuff. You just put some directives, and the whole thing feels much more natural. So, nonetheless, okay, as everything is, OpenACC is not the silver bullet. It's having a high-level representation is not always solves all your problems. Because you still need, as you're going to see, you still need to understand a bit how at least a small understanding of what's going on under the hood, because again, you might need, okay, why I parallelize my code here with OpenACC, why it doesn't go so well? What should I do? What am I doing wrong? What should I change? Because again, you need to adapt. And of course, I mean, although performance can be really high, if you're so crazy and you want the last bit of performance, then okay, you may go for CUDA. And the other thing, this was especially true some years before, but now the user base is expanding, and Mark is going to show you several success stories, and also the standard matures. And this helps also because there has been also in the past several ambiguities, and I remember running into compiler bugs in the past and things like that. So as more users are coming into the community, then this evolves. So let's now leave the introductory stuff. Yes, please.
Just a question.
Let me just give you the mic.
So yeah. OpenACC is an alternative to OpenMP. It can do what OpenMP can do, or is complementary only for GPU?
You can also, with OpenACC, just a sec, you can run also on the multicore. And we're going to show how we can try this with a hands-on. It's just a simple compiler parameter that basically you use the OpenACC directives to work on the multicore. So yes. And again, on the other hand, OpenMP, the OpenMP 4.5, they have introduced the accelerator directives that basically also you can use OpenMP to run something on the device. But there is a different set of directives. It's not the same usual OMP parallel 4 that you use. You have to use some Teams distribute and all this kind of stuff. So let's see the basic format. So directives, what is a directive? Directive is something, an instruction we give to the compiler. It's not actually real code. It's an instruction we give to the compiler so that the compiler generates something for us. So In C, this is achieved with the so-called pragmas. So if you see, pragma is something that the compiler recognizes or not. So all compilers that recognize OpenACC, they might recognize pragma ACC. Then you have a directive name, and you have a close list and a new line. And then the directive is active for the next block of code. So in C, what is a block of code? The block of code is either the next line, if you have a for loop, or the next group of lines that is grouped inside curly braces. So you can have a directive, curly brace, open brace, a set of instructions, open brace, close. Close the curly brace. In Fortran, it doesn't have the pragma concept, so you have this special kind of comments with the comment and dollar, which is like the directive, and comment dollar ACC, again, the same syntax. The only difference is, because in Fortran you don't have the notion of the block of code with curly braces, you have to also put an end directive. So the programming model, again, is host-directed execution. So the host takes care of, the directives, etc., is on the host code, and the directives instruct the compiler to generate code to move data, to launch a kernel, to wait for events, and so on and so forth. Now, let's see a bit of the terminology. So the device executes what's called two types of OpenACC region. So the parallel regions or the kernel region. So these are the two high-level concepts. So the parallel region is just a single, it wraps around a single work-sharing loop. What is a work-sharing loop? It's like a for loop in iteration space that you want to split the iterations in different threads, basically, as you do with OMP4 in standard OpenMP. The kernel region is a bit different concept, not present in classic OpenMP, where basically it's a region, we're going to see it, that you can have multiple loops inside there, and then the compiler will automatically try to generate different kernels. So OpenACC exposes three levels of parallelism. One is called gang parallelism, the other is called worker parallelism, and the third one is called vector parallelism. So what are these things? How do they correspond to what I have shown you in the first part of the course? So the gang is basically CUDA block. You remember, I don't remember we have talked about gangs before, but anyway, it's this block. So you remember we said the kernel is consisted of blocks. So these are gangs in the OpenACC terminology. Just wanted a different name to be more generic. The worker is actually the warp. And the vector is the individual thread. So then you can have an algorithm parallelized across gangs, so the iteration space is partitioned across gang. It can be partitioned additionally across warps and additionally across the individual threads. Technically, the mapping to block warps and threads is implementation defined, but currently this is what the implementations are doing. Now, let's move to the different modes of execution. This is one of the parts that it's at the very beginning of perhaps the first section in the OpenACC standard. It's always very confusing, but I have a couple of slides later to explain better, because I haven't always been confused what all these terminology mean. So we have at the gang, now at each of this level of parallelism, essentially you might actually execute in parallel or not, actually exploit this level of parallelism or not. So at the top level, where we have the gangs, which are the blocks, you have two modes of execution, gang redundant or gang partition. Gang redundant means that the code is executed the same by every gang. It's like redundant execution. Partition, it means it partitions the iteration space. Then the worker single is only single worker, that is a single warp is active. Partition means means that your iteration space is partitioned across all the warps of the block. And then vector is, again, whether your iteration space is also partitioned across the vector lanes, that is the CUDA threads, or because OpenACC can also be for multicore, it can be the vector lanes of the SIMD instruction unit. You might have on KNL, you can run on KNL, and then the vector lane will be its individual part of these 512 wide vectors. But let's see it, because it's confusing just seeing like that. So let's see the different modes. So assume we have this loop, which basically does a scale update of the B array and stores to A. And assume you have 32 by 32 blocks, which means 1K threads will be resulting. So for all this loop with 4K, in total I have four gangs, 4 blocks. Now, assuming that I am executing in gang redundant mode, what does this mean? So one thread of the block, just only one thread of the block, will execute the whole loop here from 0 to 4K, from 0 to 4K, from 0 to 4K redundantly. And that's a single little thread here. So this is totally inefficient if you are in this kind of mode. Yes, please, just to bring a mic. Yes.
Small question, I need to be sure that I'm understanding. So in this case, we have every block is 32 by 32.
Mm-hmm.
So I have 4 blocks, and this block is my gang.
Can you repeat?
So in this case,
yes.
in this example, so one block is 32 by 32
Yes.
Right? And so in this case, I have 4 blocks, which creates one gang.
No, one gang, a gang is a block.
A gang is the same as a block.
Yes, yes, a gang is a
Okay.
block. It's exactly the same.
Hmm?
The SLR code, okay. So now you can also submit jobs. Yes.
So for kernel, what is the difference between kernel parallelization and gang parallelization? Is it same or is it different?
No, it's different. By kernel, just a sec. So kernel parallelization, what do you mean? There is the idea, if I understood correctly, you can submit, on the GPU, multiple kernels may run at the same time. That's if I consider it correctly as what you say about kernel parallelization. But each kernel consists of blocks or gangs. So assuming that this becomes like a kernel function, for those known, CUDA is this with underscore underscore global underscore underscore. And then, so here you call it with, for example, the runtime or whoever, or you specifically, you can do it also on OpenACC, says that I want 32 by 32. So assuming that you have 32 by 32 blocks, which means all of these will execute this kernel. All of these threads will try to execute this kernel. Then redundantly, one single thread of each block, just one of them, will execute the whole thing. So here you're just wasting resources. Okay, that's the gang redundant mode. So let's go to the gang partitioned mode, but worker single, vector single. What does this mean? It just partitions this iteration space across the gangs. So the first gang, the first block, will take from 0 to 1K, the second from 1K to 2K, and so on. But again, since we're in worker single and vector single, just a single thread will execute this whole loop. So again, okay, we have a little increased parallelism, but not at the level that we'd like to. Do you want to ask something? Okay. So let's move to the next level. So worker partition. So this means that, again, here we have gang partition. So again, this partition doesn't change. Don't take it per se that this is the way they will partition it, just for demonstration purposes. This is compiler dependent. So the worker partition means that I will spread the work across the different workers, assuming that the worker is like that. Consists of the threads, a set of threads here. So inside each worker, a single thread will be active. Okay, so you just partition across the warps, basically. And then we go to the fully parallel stuff, which is what we'd like, and it's gang partition, vector worker, and vector partition. So this means that the whole iteration space here that is assigned to this gang will be executed by all the available threads. So basically, in this particular scenario, means that a thread will just execute a single iteration. That's very common. That's very common in GPU programming, and it's a concept that we don't have it from the CPUs and multi-core programming. We need to create parallelism. So you just create the maximum parallelism you can. So if you have a loop like that, then each iteration is independent from the other. So it can be executed by single thread. So I will try to create as much threads as my iteration space is. And then it's up to the hardware to schedule them ideally for me. So that's a different concept from, if you had OpenNP here on the CPU, like OMP parallel 4, it will perhaps do just split the iteration space like that, and then each thread will execute the whole thing. It will be like the gang partition stuff, and that's it. Here you have multiple levels of parallelism that your algorithm should be able to exploit. And in order to do that, you have to avoid dependencies and this kind of stuff. This is quite crucial. Any questions?
So when you go from worker partition and vector partition, then again the 0 to 1K loop is further divided. Your mouse or
yes.
thread,
So
okay.
each thread
it's
will
not like the one in the slide shown like 0 to K.
Assume that this is all individual threads. Assume that it has like 1K threads. So this will. So every thread will take. Yeah, I didn't have so much patience to draw proper squares.
It takes care of this division.
Excuse me? Yeah. For you, sorry. I was searching like, yeah.
And compiler takes care of this division when you just specify OpenACC or ACC parallel then.
Yes, actually the compiler will select a block size that works well for the architecture.
Okay.
And then it will determine how many blocks we'll need to create from your iteration space.
Okay.
And then it's up to the GPU to run them. Yeah. And then, but you can also, we will see that's how you can specify the different levels and when the compiler infers them and when not. Yes? What?
Could you explain again the difference between worker partition and vectors partition, like from worker partition to...
From this slide?
From this to the next, yes.
Yes, okay. So assume here that I was a bit lazy doing this, these squares here, but assume that this square has horizontal and vertical lines that are denoting the threads. So assume that each one of these lines, it is a warp, the horizontal one. So the worker partition, what it does, it basically splits the computation, partitions the computation across the warps. And inside each warp, it's just a single thread that is active. So in this case, in total you will have only 32 threads active. Whereas here, it's basically everybody is active. Also, all the warps are active, and every thread of a warp is active.
And how, so when there are only one on each? So it means when it's a single vector, so there is only one thread per, how to say?
Per
so there are
worker.
only 32 threads who are working on the 1,000, from 0 to 1,000.
Yes, yes. If it's worker partitioned, but vector single, just a single thread, yeah, in total you will have like here 32 threads that they will work on the whole.
And how do the partition, what is the partition of between these 32?
This is implementation defined, but it could be that everybody will just take a part of it and partition it. It's
Since I'm here, I don't see any fundamental difference with OpenMP. If you have, 16 threads, it will parallelize exactly this way. Don't you agree with me? For example,
I would say up to this point. Up to this point, it's basically adding a couple of more levels because OpenMP parallel is usually the gang redundant thing. Everything will be executed redundantly. If you have OMP parallel and OMP4, then you do this. It's just that it adds additional levels, and you end up basically partitioning. A single iteration is taken up by a single thread, basically. Yeah. Which, okay, in OpenACC you see, the similarity with OpenMP, but I have started programming CUDA, and initially it was really weird when in a thread you were just writing this thing and no loops. So that's why I said that it's a bit different at the very end. But the concept is, you partition. It's partitioned across. So generally, you can say that, it simply adds some more levels. Okay, moving on. So let's see now the different directives. Let's start with kernels constructs, which is the easiest one and the first basically to try. So usually you start with ACC kernels, and then when it enters the kernels, initially before finding a loop, the code executes in gang redundant mode, as in an OMP parallel directive. And then whenever you find the loop, the compiler examines the loop and tries to infer to check if there are dependencies of loop carry dependencies and stuff, and it decides on its parallelization. It's like automatically parallelizing. This is the easiest way. You have a large set of loops, and you just put a kernels around it, and you see what the compiler produces. And then each of the individual loops will be launched as a different kernel, and you can check the compiler diagnostics. We'll see how to see whether it has parallelized the way you want it or not. So the next is the parallel construct, which is it is bound to it is bound to a single kernel. So the whole parallel construct will not generate multiple kernels, but it just generate one kernel, and then you partition your loops with the ACC loop directive. And here the compiler does not deduce any parallelism. You are controlling it, basically. So again, when it enters, the whole thing executes in GR mode. So here I have not put any ACC loop. So the whole loop here, the compiler will not try to understand, okay, here I have a loop. Let me see if I can parallelize it. No. We'll just listen to what you ask him to do, and we'll just execute it in gang redundant mode. And here, you can just specify ACC loop, and then the compiler will analyze the loop and will infer, depending on the dependencies, on which mode. Of course, you can force the compiler to follow a specific parallelization. And another thing is that there is an implicit gang barrier at the end of parallel, meaning essentially that the kernel finishes and the host code waits for the kernel to be finished. We shall see tomorrow how we can avoid these things, so as not to wait. Okay, so work sharing loops. Again, we've seen already the AC loop directive, which applies to the immediately for loop or to the immediately following do loop for the Fortran. Notice here that there's no end loop directive, as far as I remember, because you have the do loop so in Fortran as well, so the scope is clear. And then the loop will be automatically striped and assigned to different threads. And if the compiler sees a dependencies that always the compilers are conservative. So if they are not safe to parallelize something, they will step back. In that case, you can also say that these iterations are all independent by adding this clause, the independent clause here. Then you can also combine as convenience, when you have a parallel and then a loop, as in OpenNP, you can do parallel loop here or AC kernel loops and combine them together. So here we have a nested loop where we're using the collapse keyword. Perhaps you have seen it also in OpenNP. There is a small difference there. So actually in OpenACC, it's not exactly the same as in OpenNP. OpenNP basically collapses the iteration spaces. And here it applies the AC loop also to the internal. It's like saving space for writing it and perhaps collapsing the loops. Generally, this is a difference between the two. So OpenNP is more prescriptive. So you specify exactly what the runtime should do. OpenACC is a bit more descriptive, I would say, and you let the compiler do some stuff and allow him to do optimizations for you. That's a fundamental difference in the concept of both. So how you can control parallelism? So you can, of course, specify using these clauses, num gangs, how many blocks you want to create, and then the compiler will infer perhaps how many workers, etc., or how many workers you want, or how many, how large is your block size, basically, the vector length. And you can also specify, as I said, on the loop level, these three clauses which say, okay, this loop should be partitioned, should be run in gang partition mode and vector partition mode. So parallelize it full. These are usually, these are not needed unless you have dependencies and you want to force it, because most of the times you will see it also from the diagnostic messages that the compiler automatically recognizes the loops and produces code for as gang vector, etc. So the maximum parallelism. Here, for example, we create 100 blocks of 128 block size. Okay, so now what about the variables? It's only relevant for the parallels construct, and by default, if a variable is defined as outside parallel region, then it is shared among all the gangs, effectively meaning that this should reside in the global memory. It's to give you an understanding of also performance implications. However, if a variable is private, then it is placed inside each of the blocks in gangs. That effectively means that it could be either in the shared memory or in the register or something, depending on the compiler. First private, again, like OpenMP, same as private, but takes the initial value from the host. Now, there is also some implicit scoping rules for the loop variables. So loop variables are private to the thread that executes the loop. So basically means that they are in a register, well, apparently for efficiency reasons. And now the other thing is scope of variables declared inside the parallel block depends on the current execution mode of the block in C or C++, where it will be placed. Okay, these are a bit of details, but it's worth to know because it might incur costs, especially when we want to optimize. So we have also reduction operations as in OpenMP, and they also go on the parallel section. You cannot put them on the kernels, if I'm not mistaken. So an example is here, reduction, the operator, and this is a variable. So the variable must be scalar. There are discussions, I think, to support also array reductions, as in OpenMP. Now, the var is copied and default initialized within each gang, which means the default initialization, basically, the variable is on each gang. You get a copy on each gang, and depending on your operator, it will be initialized to 0 or 1, so as to the neutral element of each operation. Now, then intermediate results from each gang are combined and made visible to the assigned parallel region. And this is what is supporting the different operators. And actually, reduction, if you were writing this in CUDA, you had just write a reduction kernel in CUDA that would reduce the values of an array. Is not as easy as it seems. Here it's just a single line that you put on your loop. And in CUDA, you would have to do this gathering of intermediate results from each gang yourself. And that's not so straightforward. Okay, so another important directive is the routine directive, because it's very common the case that you want to call a function from inside your parallel region. So, but the compiler sometimes cannot infer from what level of parallelization this function will be called from. So there is this directive called ACC routine, which in C you put just before the function declaration or definition, or in the specification part of the routine, and you specify that this routine is meant to be called by a gang redundant context, or a worker single context, or a vector single context, or from a single thread. So then the compiler knows that you call it from that type of context in order to generate the corresponding function on the device. Actually, also the latest PGI, not the latest, from some time, the PGI compiler, they infer the context from which you call a function and automatically produce a version of the function without having to specify the routine directives. Okay, so let's move to the data management. Any questions so far? Yes.
Just a short question about the reduction, because usually when I've done the reduction with CUDA, it makes only sense to do it up a certain array size. Is OpenACC smart enough to extract the array and do the rest on the CPU?
No, you can, even in CUDA, this is the initial implementation to be, oh, sorry, wrong button. The initial implementation is to be up to a certain array size. You can do it with arbitrary sizes in CUDA as well. But OpenACC, you can do it in arbitrary sizes. It's smart enough to do it for any array size. You're not bound for. But you're saying you.
That is not the question.
Oh, okay. You said you do.
I meant at the end.
Can you?
At the beginning of the reduction, you have a huge array, and as you are reducing away, you are halving your array over and over again. So in fact, you are reducing the number of threads which are effectively doing anything, so at least something. At the end, lots of times it doesn't make sense to run it on GPU at all because there are just 100 threads.
Okay, I see. Yeah, I don't know the internals how they implement it, but I suppose that they're doing in an optimized way. I don't know exactly how if they run parts on the CPU, this combination of results, but at least up to a certain point, they might be running this on the GPU.
Okay.
So, yeah, sorry.
So can you once again clarify difference between routine, kernel, and a parallel region? What is the difference between these three?
Okay, yes. So the kernels is the most generic construct. So it's like marking a large region and telling to the compiler, go ahead and extract any parallelism you find. So the compiler would just go and find the different loops, see if it can parallelize them, and will create multiple kernels. For example, each kernel for each of the loops. The parallel region, you just say to the compiler, the whole this region is a single kernel, go and execute it, and the way I say to you. And it won't try to infer any parallelism from the loops you have inside. You have to specifically put a loop directive and say to the compiler, okay, this is a work partition loop, so go ahead and partition it across as many threads as you can. Now, the routine is a different thing. It's just, I would say, declarative, somehow directive, that you basically use to say that this routine may be called from a sequential context, which means that whoever calls that routine, it's a single CUDA thread, for example. It executes in vector partition mode. So the work in the loop is partitioned across the single threads, and then if a thread there calls a routine, then that routine should be marked as sequential. And similar stuff for the rest. So it's different things. Is it not more clear? Okay.
I mean, let's suppose I would just put in each thread the 1 + 1, and I run it first with the CPU, and then with this model. Is it like at which stage does it become worth to use?
Okay, good question. The answer you will see it in the hands-on sessions, but wait a bit also to see the next part. Yeah. So to answer, in a better way your question, you will see it. if I understood correctly, is does it work to use to parallelize a kernel with OpenACC than just run it on the multi-core, basically?
There must be some overhead of...
Yes. I hold that question by showing you a bit the next part, and also we're going to see it in the hands-on session live. We can play around. But I will, during the presentation, I will specify the key parts so that you can understand this. So, moving on to the memory management. Again, as I said, the OpenACC programming model follows the architecture model, which is the separate address spaces. So the data management between host and device. So the data management is the programmer's responsibility. So you have to take care that all the necessary data of your kernel is on the GPU when the kernel needs that. Otherwise, you will have problems. And then as soon as you finish, then you should make sure to transfer back the results that are of interest to you. Okay, but there's also the alternative model, and there's also we're going to see it also hands-on sessions and how this is supported. Now, the device might also be the multi-core, in which case there's no such thing as a separate address space. So the data directives, they have no effect. So they don't move data around because they are all in the memory. They're all present, the data you want. The other thing is sometimes you may omit completely the data transfer directives, and the PGI compiler will analyze your loop and see, okay, here I should I should copy in that data or copy out the other data. This is very handy, but for our exercise at the beginning at least, I think it's good to know a bit the data management directives. And as I said, the NVIDIA Pascal GPUs, which we have here, provide a unified memory view, in which case you can completely omit the directives and have this page migration happen by the hardware. We're going to see how this happens. Now, and so see now how it happens, the whole kernel execution. So as I said, we have two separate address spaces, the device address space and the host address space. Assume that these are the pages corresponding to an array we're using, a large array, and this is another array. So first of all, I want to run a kernel that basically works on both of them. So it reads from the red one, and it reads and writes from the orange one, if I remember correctly what I have done afterwards. So first of all, you need to copy in the data from the host to the device. I need this. I also need to copy in here from the host to device. Any idea what is the interconnection network between the host and device? It's PCI Express. Any ideas of the bandwidth? It's up to 8, at least for the cards, we have 8 gigabytes per second. Any ideas of the memory bandwidth of Haswell, or a modern Intel architecture? The CPU you're running, a high-end one, a server? 50 gigabytes. So this is a hint for the trade-off of the data transfer. So you need to transfer it. And then you call your kernel, and now the kernel touches those two data. This automatically, not automatically, in effect, it has invalidated those because here you have your new data, okay? So you should make sure, but it's the programmer's responsibility, this synchronization of data. If you want to get the updated data, you have to copy it yourself. It's not going to happen automatically. So that's why I was saying also at the beginning that you still need to understand the programming model in order to even program in OpenACC. So then my kernel finishes, and then I need the data, and then I copy out. And this also in the OpenACC, if there are no other references to this region, it will also destroy that region. So as not to occupy space on the device. Then I launch another kernel. Now, that touches this data. Now notice the following. That this data is persistent. So I copied it at the beginning. I launched one kernel. I finished, I launched another kernel, and the data was there because I haven't copied out or deleted or anything. That's important because this is the way to avoid unnecessary copies. So I'm running this kernel, touches this data, and then I copy out also this, and here it comes and removes it from the GPU. Now, OpenACC takes care automatically of the deallocation, so you don't have to CUDA free to free your data. It will be garbage collected in a way. Yes.
You are saying is it copying, but it looks like you're moving, right? So because if it's a copy, after the kernel has finished, we can just remove the data in the device.
It's up to you how you manage it. So here, oops. So here I'm copying the data, then the kernel modifies it, and this basically has stale data.
Okay.
So the data is still, there is a copy. I mean, you copy it.
So the old
here, yes, it's kind of the old data.
Yeah, okay.
But it's still there. So you need to make sure to update it yourself. Mm-hmm. And as soon as you copy out, then automatically, if there are no other references there, then it will remove it.
Is it possible at all to copying data and running a kernel at the same time?
Yes, and we will see that tomorrow.
And just one more comment on that. Those of you who might have programmed CUDA, where you will use different variable names typically for your host's version of an array and your device version of an array. One of the slightly confusing things when you look at source code with OpenACC is these things actually coexist and have the same name. So if that orange array would be array A, and you'd be going through your source code, whenever you're in the CPU part of the code, the version on the left is what you'd be using, and it could be out of date if it has been modified on the GPU. And if you're inside a parallel or kernels region, you'd be using the version on the right, but they have the same name, although they live in different address spaces. So that's something that takes a little bit of getting used to. And if you're coming from CUDA, it's a little bit confusing that you have the same name instead of two separate names for that.
Yeah, very good point. Very good point, yeah. Yeah, we will see that in the directive syntax, but it was a very good point. So now let's see the other way, the unified virtual address space. So here you have, again, you have two different physical address spaces. So on the host, again, you have your array allocated here, your array is allocated here, but all of them are seen programmatically as a huge memory area that you cannot separate whether it's on the CPU or on the device. So you don't care about data management at all, and you just launch your kernel. And then your kernel tries to access a pointer that basically refers to the host addresses. And this will create what we call in the OS terminology a page fault, because I cannot find the page you requested on my address space here. And then the OS takes care of that and serves your request. and it says, okay, I will transfer the page you asked. Here I'm transferring multiple, but the idea is you transfer the page that you faulted on the device. And then the kernel can use, okay, I don't have another slide. And then the kernel uses the copied versions. And the same happens the other way. So when the host here touches those stale now pages, those pages will be migrated back. So it's really helpful in terms of programming, and we're going to experiment with that in the hands-on sessions. And it's also very, very effective, but it can be cases that you actually need to do your data management yourself with. But the hands-on session, you will see they're not so difficult or complicated. And keep in mind that this needs OS support. The kernel driver must support it, and there must be hardware infrastructure for this to happen efficiently. Because the unified memory as a concept was introduced by CUDA in, I think, CUDA 6 with a previous two architectures before the current one, the Kepler. And there, this was not efficient at all, because there was no way, I mean, the granularity wasn't at the page level. So every time we're trying to use that feature, then the whole allocated space you had was copied over to the host and then back to the device and back to the host. But here, the Pascal architecture and forward, they have special hardware to support page faults and then facilitate that migration, as it happens with the OS systems on the CPU. Because this feature won't work in older GPUs as efficiently as now. So let's see now the data directives. So the data clauses. So because there are some data directives, but also what we call clauses. Clauses is the additional part that follows a directive. So the data clauses, you may have them in the following two directives, where you specify what should be copied in, copied out, etc. And then you have some specific data directives. We're going to see all of them one by one. Okay, so here are the data clauses. So first is the create. So basically, you ask to allocate an array. It's like allocating an array on the device of size n. We're going to see the subscript index just in the following slides. Then you have the copy in and copy out. Is copy the array A to the device and then or copy out from the device. Now, in the first versions of up to OpenACC 2.0, there were also the p copy in and p copy out, which was like present or copying. So if your data was already copied in before, it wouldn't be copied. But now from 2.5, the behavior is of copying is always like, if it is present, then don't do anything. If it's not, then copy it in, and vice versa. Now, the copy out, all these are associated with, all the data regions are associated with two set of counters that they are doing actually reference counting, so that when you copy out, when those counters reach 0, then the data on the GPU is garbage collected, so that you don't leave stale data there that's just uses up space. The copy is the combination of copy in and copy out. Present is you just say that you inform the OpenACC runtime. You're saying, okay, look, this array have already copied it in before, so you have a loop and you say, okay, the arrays you see here are all present, so you don't care about copying them. I have copied them in a different place. And then you have the delete directive, which basically deallocates the array from a device, and it can only follow the exit data directive. Now, these data clauses are not for the ACC update directive. Let me see if okay, I have it also here, but we're going to see exactly what they mean. Okay. So, now, these data clauses, they're I mean, we said that this data clause can go to the kernels and to the parallel. So you can have a kernels region or a parallelism saying copy in my array there, and we will copy in or copy out the result. They can also go to this specific data directive that's called ACC data, which just does data management. So it's just like having this data directives that basically is just copying data. You don't launching any kernel at all. And this is useful when you want to move as outside as possible or as early as possible in your code the data movement, so as to then just do computations. So it's AC data plus the data clauses we've just seen before: copy in, copy out, present, and so on and so forth. And again, the next block of code for C++ or until an end data is encountered. Now, the AC data directive, as I said before, associates important thing. The data will be copied in or created at the entry of the region. So the time you see this directive, then the runtime, the OpenACC runtime will insert some code there that will basically go and copy the data. And the data will be copied out or deleted or acted upon, but generally let's say copied out, when this region ends. So after that region ends, then you know that the host has the updated values. Okay? And another thing is, as I said, because of this garbage collection, all these data, scoped data regions, and they're referred to as scoped because they have a scope. You have a begin and end that you must be in the same compilation unit, or in the same function, I would say. They have what is called a structural reference count. So every time you do a copy in of a data, this structural reference count increases. So then the runtime can keep track of how many people are referring to this, so that it cannot delete it and basically invalidate other parts of the code. This is typical garbage collection stuff. Now, let's see the other two directives I have presented before, the enter data and exit data. These define an unscoped region. Why this is useful? This is useful because with a scoped one, you're kind of confined in a single function, basically, because your data movement will happen at the beginning of when we see the directive, and will need a corresponding end block that will basically copy the things out. Here are unscoped. So at any point of your code, you can add enter data and exit data. So this allows you to do data management across compilation units. So you might have some global data that you want to move, or in a function, some data that's in one file, in a function in one file, you enter the data there, and then in another function you exit. This is really useful. Tomorrow, in the deep copy hands-on session, I have an example with a C++ object that resides on both the CPU and the GPU. And this happens completely transparently to the users of that object. You will see that. And also, this is associated with a dynamic reference count. And again, this is for garbage collection. So whenever the structural reference count and the dynamic reference count for a specific region have gone to 0, then that region is wiped out from the device. So this is how it is. So enter data clauses, the data clause we've seen before, plus the next data plus the delete clause, which can only be in this exit data, and in Fortran accordingly. Now, there is another data directive that's called declare. And so this is Yeah, this is a bit, about the, mostly for global, for copying global variables to the device. So basically, you declare that the variable is already, must be also created on the device, and usually you use it for global variables. This we're not using in the exams, but it's important to, it's good to know. Okay, a quite useful one is this one, the update. So the update is just does moves, not moves, copies data. Basically, I would say synchronize the data you have on the host with the data you have on the device and the vice versa. It does not affect this reference count. So you just, the data still resides on the device with its own reference, you just doing an update call. So yes, these are quite useful because it's very common that you have put your stuff on all your arrays on the device, you do your kernels, and at some points you need to report some results, you need to do some stuff on the CPU, then you just say update host to get your data back. Or you can, after you compute something on the CPU, then you just want to move it to the host. There is a typical scenario for that, if you can imagine. Can you imagine? It's MPI. So you compute something on the device, then you want to communicate that data to a different process. So you have to get it back from the device, then communicate it. And as soon as you receive it, then you have to communicate it to the device. So move it from device to host, send it, receive it, move it from host to device. Tomorrow we're going to see more optimized path to do it. But in principle, this is what you would do and what you normally do for open support of MPI. So these are quite important. So, array ranges, because you've seen at the beginning that I had this ACC, create, A, and then square brackets. Now, I'm starting from Fortran, because Fortran, you just put the name of your allocatable array. And that's because allocatable arrays in Fortran, they already have a shape incorporated to the data type, so the compiler knows how large is the array. In C, you have to specify from 0 to n, so you have to do that because there's no shape, it doesn't know about the pointer, how the region it refers to. Now, except that if you have a present directive, it suffices also to put the pointer, because the pointer there, as soon as you have copied in, then the runtime knows that it has already internally an association of, okay, that pointer on the host refers to that pointer on the device with so much size, because you have done that in copying directive. So here it suffices to put just present A is acceptable. Although I think it's, formally, I think you may also have to put brackets, but it's also acceptable, I think. And also you can have this kind of thing, so you can copy parts of an array. Okay, yes?
So copy in via slice, it also works in Fortran?
What?
So copy in a slices, it also works in
yes,
Fortran?
yes,
Okay.
yes. Okay, so synchronization directives generally. I said you can't synchronize all the threads of a kernel. There are no such concept in any case. This synchronization happens across kernels. Nonetheless, you have support of atomic operations, which you use this syntax, ACC atomic, and you have read, write, update, or capture, where capture is this complex operation which comprises of two operations, v equals x, and then plus plus x. So this is like the capture. I capture the value of x, and then I incremented all this happening atomically. And there's also no equivalent of sync threads, as those that you might see in CUDA. And the reason for that is that basically I don't think you need it, because you can control that implicitly from the levels of parallelism. But it's because the runtime, depending on the parallelism of the loop, it will put such things like sync threads in order. For example, if you just had, if you didn't have a vector partitioned loop, but you have a worker shared loop of vector single, then the runtime will insert the sync threads accordingly to make to meet the desired parallelization. Okay. So what do you have here? Okay. So again, as I said, as I showed you before with a unified memory, you can omit completely. I mean, the hardware can take care of the page migration, so you can effectively completely omit the data management directives in OpenACC. You can achieve that by passing this flag to the PGI compiler. Actually, this is only supported currently from the PGI compiler, and I would say it's quite useful. And we're going to see it also in the hands-on session and play a bit around with it. So I think this, yes. So this finishes the basic directives. So just to summarize, we have this host and accelerator device model. You should always take care of the data management. Okay, I leave a bit aside the unified memory because I think it's important to understand the data management. And then you have this the basic construct, which are the kernels, the parallel loop, and then the parallel and then the loop, and the different levels of parallelization. And then you have the data management, where the key clauses are the copy in, copy out, and create, I would say. Then you have the data management directives and the update, to update data back and forth. So it's not the standard is not huge. This is all the basic stuff that you can start now implementing simple kernels on the GPU, and you will see it's fairly easy. So, any questions so far? Okay, so now I'm gonna present briefly. Yes.
So, if you want to transfer data between threads, how do you do it? Between threads in GPU? You just do it via index assignment?
But what do you mean transfer threads? I mean, in what
or
sense?
access the data between threads from different gangs. Is it possible?
From different gangs? No. Okay, you can have a global array.
At the gang level.
If something resides in the global memory, then all the threads can see it, all from any gang.
But then it's less efficient, right?
Yes, because otherwise, then the sharing is just at the gang level.
Okay.
So, okay, I'm gonna just quickly introduce the hands-on examples. So here is the repository to clone. So everything is there, and also the slides, everything. So here you just clone this, and whenever we do an update, for example, at the end of the course, I'm gonna push the solutions there. So then you just simply do git pull origin master to get the latest master. Okay, so, and then, I mean, for future reference in that repository, I create releases to keep track of the different versions of the lesson. So later on, I mean, this can, if you do git pull origin master after, I don't know, 3 or 4 months, suddenly your solutions might go away. So you can just copy it right now and have them. And then the structure is as follows. Here is the practicals, where are the hands-on exercises. There are several subdirectories in there, and I'm going to give you instructions on how to compile, run, etc. Here is a couple of shell scripts that you will need to source just to make your life easier. And it's also because we're going to work with the latest PGI compiler, the 18.4. And actually, this is provided by us, not by Cray. So as soon as you source one of those scripts, then basically you cannot switch back to PRG and Cray if you'd like to. Then here is the slides. So I have uploaded all the slides of today just to follow up, and then I will do that also for tomorrow. And now the CI is just basically is for me for testing, is a set of continuous integration script that basically runs to make sure that all the tests, that all the exams are fine. If you're interested, you can ask me offline. Okay, so now the general motif of the hands-on is the following. So there are to-do comments. So if you grep for to-do in pick up your language, Fortran 90 or C++, unfortunately, some of the advanced exams tomorrow, one of them is only Fortran, but we have another that's only C++, and another one is just C++. But in any case, we're going to walk through them later on. So you will get an understanding. Didn't have the time to implement the Fortran version. As I said, this is the script to set up the PGI 18.4. As soon as you do it, there's no way back to go to PRG GNU, PRG Cray, because this is a bit custom solution because it's not natively provided by Cray, the latest version. But theoretically, the today's hands-on session will work also with Cray compiler. So it's not necessary to do this. But I suggest you do, because we're going to play a bit also with the managed memory. So that could be. Another thing is you need to load these packets, CrayPXL NVIDIA 60, which basically set the target architecture to the GPU, and also load the CUDA driver, the CUDA runtime, so that the PGI compiler then can find it. And we always provide make file, so usually you just do make, and that's it. And if you happen to use the Cray compiler, you should do make verbose equals 1 to get all the messages. For the PGI compiler, I'm always splitting the messages about the accelerator, and then you can see which parts were offloaded to the accelerator. Okay, so if you have any questions, for the moment, I would ask you to, if you don't have any questions, just to make sure that you can submit jobs and stuff, and make sure that you all can do that. And then, okay, we are like 10 minutes earlier. And next session, I was thinking to present you briefly about debugging before going to hands-on sessions. So for the moment, I suggest you just make sure that you all have access to the reservation, that you can submit jobs, and just let me know if you have problems.